Hello everyone. Today I'm going to talk a little bit about some recent work that I've been doing on unsupervised word segmentation from speech. So I've been working on this task for quite some time. Basically the idea is that we want a model that can take a corpus of unlabeled speech audio where we don't know the language, we don't know the words that's being said, and we want that unsupervised model to tell us where words start and end in the speech stream. If we can do this, if we can solve this task, then that would allow us to build speech technology in languages where it's currently not possible. It can also be a way to get some insights into how human infants acquire language, their native language, by being exposed to unlabeled speech data, in addition to some other cues that they might have. So the methodology that I'm going to employ today, it's inspired by much older work. I'll say something about that a little bit later. And basically the idea is to take your unlabeled speech and then use some model to convert that unlabeled speech audio to a sequence of acoustic units. These are units that mimic the phonetic inventory of the language. Then what we'll do is, on top of the sequence of discrete units, we'll apply an unsupervised symbolic word segmentation approach. So this is an approach that in some way looks for repeated patterns in the symbol sequence and then hypothesizes word boundaries between places where it thinks a word boundary should occur. And if you glue these two things together, bottom-up unsupervised acoustic unit discovery at the bottom, and then following that with symbolic word segmentation, then implicitly what you get is you get hypothesis for where boundaries start and end in the speech stream. So I'm going to use this older methodology. It's something that people have tried before, but I'm going to explain two new models, one for unsupervised acoustic unit discovery and then the other one for symbolic word segmentation. And then I'm going to glue these two models together and see how they perform for speech segmentation. I'll start by describing the unsupervised symbolic word segmentation approach. So let's say we've got some autoencoding recurrent neural network. This is a encoder-decoder model that reads in a sequence of symbolic units, and then that's through the encoder, compresses that into a fixed dimensional representation, and then the decoder outputs another sequence, and the model is trained so that the output matches the input. For this part of the talk, instead of talking about acoustic units, I'm just going to replace that with letters so that we can kind of see what's going on. But every time you see a character, just remind yourself that it's actually an acoustic unit. Now, let's say I give you this autoencoding recurrent neural network. And so I'm not telling you now where it comes from, but I give you one. And this AE-RNN is good with some inputs and less good with other inputs. So for instance, let's say the input is time. Then I can calculate a score for how accurate this AE-RNN is with basically compressing the word time by looking at the output probabilities at each of the time steps and taking the product of the output probabilities over the output sequence. If I fed this AE-RNN with another sequence, maybe this one, ONG-T, then I could get a different score. And maybe in this case, the AE-RNN actually gives a very bad score because it models this sequence badly. Now we can use this property of the AE-RNN to actually segment input. So let's see how that works. So let's say I give you a longer sequence, maybe this one, a long time without the spaces. And let's say I propose some segmentation. Let's say I propose that it consists of these 5 words. Then what I can do is I can feed each of the segments into my trained AE-RNN and get a score for that segment. Okay, I can do that for each of the 5 segments in my sequence. Okay, and in this way I can get an overall score for that segmentation according to my autoencoding recurrent neural network. If I had proposed a different segmentation, let's say I proposed this one, then I would feed in each of the segments into my AE-RNN and I would get a different overall score. And the problem then becomes finding the segmentation which gives us the best overall score through the AE-RNN. So is this segmentation better or is this one? And actually what I want to do is I want to consider all possible segmentations and then pick the best overall segmentation. And this is where that last DP in DPDP there in the title comes from. That last DP stands for dynamic programming. So we're going to use dynamic programming to find the optimal segmentation out of all the possible segmentations within some constraints. So maybe we say that all words needs to be just 4 characters long or shorter than that. So that's what the second DP stands for. The first DP stands for duration-penalized. And the reason for this is that there's actually an easy way for the AE-RNN to hack this problem. If you have an AE-RNN that just places a lot of mass on the first symbol that it sees in its sequence, then when you do dynamic programming using that AE-RNN, you'll just end up putting each of the symbols into a word of its own. So severe over-segmentation. So what we do to combat that is we introduce a duration penalty. And that's how you get duration-penalized dynamic programming. Okay, so the segmentation is basically the same as finding the shortest path through a directed graph. So if we assume a maximum duration of 4 symbols, so your longest word can be 4 symbols, then the graph actually looks like this. Each of the edges in the graph has a weight that you get from the AE-RNN. So we use the negative log likelihood for that edge weight. But we also add the duration penalty to each of the edge weights. So that's where that W duration comes from. There's several options that you can use there. I use a very simple linear penalty, which encourages longer segments. I also in the paper tried using a probabilistic duration prior basically to score the duration of different segments. So if you've got your segment score and you've got your duration score, then for a particular path, such as this red one, you can get an overall score. For a different path, you would have different edge weights and you can get a score for that path. And the problem is then to find the best overall path out of all the different options. And we can do that using dynamic programming. Okay, so pretty simple. There's one big question. Where does the AE-RNN come from? And here we've got a number of options. The one option is to iteratively refine the AE-RNN. So you start with some random segmentation, just placing boundaries randomly, and then you train an autoencoding recurrent neural network on top of those random segments. Then you can use that AE-RNN to do duration-penalized dynamic program segmentation. Okay, so then you get new segments. Then you can retrain the AE-RNN on those segments. Then you can do DPDP segmentation, retrain the AE-RNN, and so on. You get the idea. The other option is to use a probabilistic approach to sample likely segmentations, and that could maybe help you explore the space of possible segmentations better. And this is actually the approach used by Michael Elsner and Corey Shane in their model. And I should add here that the approach that I propose, this DPDP AE-RNN, can actually be seen as just a simplified version of their approach. So it's making hard decisions. It doesn't have this probabilistic sampling of likely segmentations. So my work was heavily inspired by theirs. So we've got these two options, iteratively refined, probabilistic approach. I tried the iterative refinement approach. I tried to apply their approach on my discovered acoustic units, but I really struggled to get it to work. So then I did the dumbest thing ever, which is to just take the full encoded sequences, like the full-length utterances that have been encoded with these into these acoustic units, and then I just train an AE-RNN on those full-length sequences. I train the AE-RNN, that's then my AE-RNN, and then I apply DPDP on top of that. And this actually works the best out of the different options when you're segmenting acoustic unit sequences. I'm not exactly sure why, but I think I can speculate on some ideas, but I think this requires a bit more investigation. Cool, so we've spoken about the unsupervised symbolic word segmentation approach. And now what I'll do is I'll talk a little bit about an unsupervised acoustic unit discovery approach. This is work that I did with a PhD student, Benjamin van Niekerk, and we presented this in a paper at ZeroSpeech. Now, what will be interesting about this approach is that it again actually reduces to DPDP. It's again just a dynamic programming with a duration penalty, but the scoring function is quite different. So let's see how this works. So in this case, you start with some self-supervised encoder. You can think about a CPC model, and this model outputs some continuous features. What we are going to do is we're going to quantize those continuous features by using a learned code book. So this means that each of the feature vectors are going to be assigned to one of the codebook entries. But instead of doing that independently for each frame, what we're going to do is we're going to propose a segmentation, and then each of the frames within that segmentation needs to be assigned to the same code. So on this figure, for example, there's those 3 middle frames. Those are all assigned to the orange code. Okay, that's how one possible segmentation works. I could have proposed a different segmentation. Let's say I proposed this one. Then my optimal assignment from frames to codes would look different. But what we can now do is we can say, is the segmentation on the left or the right better? And the way you can compare them is by calculating the sum of the squared distances. Basically adding up the squared distances of those arrowed lines. And in this case, the left segmentation will clearly be better. And the problem then becomes finding the optimal segmentation. And you can guess how we're going to do that. Again, we're going to use dynamic programming to find the best segmentation for us. The result is an encoding of the speech into basically the cluster indices for the different codes as they're selected. Okay, so we're going to do dynamic programming, and we're also going to add a duration penalty to again encourage longer segments so that we don't end up with this trivial over-segmentation solution. So we've again got our segment weight and our duration penalty, but here the segment weight is calculated on top of continuous features, not characters or not symbols. And instead of using an AE-RNN to get the overall segment score, we're going to use the sum of the square distances to the code to which that segment is assigned. And if you do this, then again we can solve this problem using DPDP. Okay, so I've talked about a new unsupervised symbolic word segmentation approach, and then I spoke about a new unsupervised acoustic unit discovery approach, and now I'm going to glue these two together. Now I should say here that it's important to note that the unsupervised acoustic unit discovery, that step is purely bottom up, and then the codes are obtained, and then that's fed into a symbolic word segmentation approach. The word segmentation can't actually feed any information back into the unsupervised acoustic unit discovery method. And this was something that this idea of using bottom-up discovery followed with symbolic word segmentation was already applied way before. So for instance, in the 2012 Johns Hopkins University workshop, they tried this approach where they tried to glue together an acoustic unit discovery with the symbolic word segmentation approach. It didn't work at that point because the acoustic units were quite poor. So this idea, bottom-up discovery, symbolic word segmentation, that has been tried before. All that I did here was basically propose 2 slightly newer discovery and segmentation methods. You could follow a different approach. So actually, since that workshop, a number of groups have rather opted for a joint approach where phone discovery and word segmentation are joined together and basically occur at the same time. So 2 very recent approaches that have gone that route is the segmental CPC model and the multi-level aligned CPC model. They're both quite similar, so both of them have a CPC-like layer at the bottom, contrastive predictive coding layer at the bottom, which does something like phone discovery. Then both of them have an intermediate boundary detector that's differentiable, that's important. And then on top of that, they have some higher level CPC model that models something like words. The important thing is these models are trained jointly. So that means the top word level CPC model can influence the bottom acoustic unit discovery layer. I'm not actually arguing that the bottom-up approach, the kind of chained approach that I propose, where you do acoustic unit discovery, it's fixed, and then do symbolic word segmentation. I'm not necessarily arguing that that's superior to the joint approach, but what we'll see in a second is that it is competitive. It gives similar results. So I think in the unsupervised speech processing community, we shouldn't discard that bottom-up approach. Okay, so let's see what the results say. So here you can see the English Buckeye evaluation results. I report word boundary, precision recall F1 and R value. R value explicitly penalizes over segmentation. And then I also report word token F1. This is where to get credit for a word, you need to get both boundaries right without an intermediate boundary in the middle of the word. And I'll just go from the bottom to the top. So the bottom there, that's the proposed chained approach where you use CPC with a k-means clustering model to discover acoustic units. And then on top of that, we use the DPDP AE-RNN to then discover something like words. The two models above that, the segmental CPC and then the multi-level aligned CPC models, you can see that their scores are pretty good. In fact, the multi-level aligned CPC model gives the best precision and R value, while the chained approach gets slightly better recall and F1 scores. So it seems that the DPDP chained approach is competitive to these state-of-the-art word segmentation models. Just for reference, those top two models, they're from some of my own older work. They try to circumvent this issue of should we first learn phones and then words, or should they be learned jointly. They basically come around this by just directly modeling whole words. And you can see there that we've come a long way from those models and most of the other approaches, but the joint approach and the chained DPDP approach outperforms those systems. I also applied this DPDP approach on French and Mandarin data from the ZeroSpeech 2017 and 2020 evaluations. And here you can see that we actually get some of the best reported scores on these benchmarks. So it's clear we're learning some interesting things here and that the chained approach does give reasonable performance. What are the types of words that it does well on, and what are the types of words that it struggles with? So here I've got a plot at the top. I show the token recall, but for each individual word type. And the top graph shows the words with the highest recall, and the bottom plot shows the words with the lowest recall. If you just read through them, you can see that the words that it does well on are shorter words. They're often filler words. I'm just going to sneeze. The top words, you can see if you read through them, they're often shorter filler words, and they get pretty good recall. Has a recall of just close to 85%. But then if you look at the word types on which the system struggles, you see that they're often longer words. If you read carefully, you can also see that a number of those words end on "ly." So you've got basically, actually, exactly, and so on. And if you manually inspect those segmentations, you'll see that the system often puts a boundary just before that sequence of "ly." So in the phone preceding "ly," somewhere there that it would put a boundary. As one example of that, here is one example segmentation. So at the top there, I've got the DPDP CPC acoustic units. So those units 1826, those are the acoustic units. And then the dark black lines, those are the places where the AE-RNN places word boundaries. You can see it does reasonably well, but the interesting mistake is right at the end there. So you can see that it actually gets the first boundary for weekend spot on, but then it places an intermediate boundary, which is wrong. But you can see it actually splits this word into week and end, which is, I guess, reasonable. So what I've argued in this talk is that bottom-up acoustic unit discovery, followed by symbolic word segmentation, should still have a place when we're trying to segment speech in an unsupervised way. It's basically been disregarded a little bit over the last few years, but I think it needs to be revisited. It could help us answer some questions about how infants learn language and whether they actually do phone discovery in a bottom-up way before or after or during word segmentation. So I think it allows us to do that. There are some shortcomings of the DPDP approach itself. The one is that the duration modeling is very coarse. I use the same duration prior irrespective of the acoustic unit or the word that you're in. So you could maybe have per unit duration models. And another issue is that it doesn't actually discover a lexicon. So the DPDP AE-RNN, it can tell you where words start and end, where it thinks words start and end, but it can't actually tell you, oh, I think you're in this particular word. So it doesn't infer word categories. Kind of taking a step back, I think although the performance is starting to get good, the results are still actually quite poor. So word token F1 scores are around 25%. The other interesting thing is that this chained DPDP approach gives quite similar performance to the joint CPC models. So this could maybe raise the question, well, are we reaching the limits of what we can do just from unlabeled speech? Maybe it's not possible to do better than this. There are maybe some inherent limitations to doing this just from unlabeled speech audio. And in the natural language processing space, there's been a lot of arguments that unsupervised language modeling can't enable a model to actually understand what's going on. You need some grounding signal. And maybe that's also the case here. Maybe we do need to get some other external top-down signals in order to segment speech. For instance, from other modalities like vision. So maybe we need visually grounded speech models to start to do this. And we know, of course, that infants do have access to other modalities when they're learning language, to cross-situational cues that allows them to ground what is being said. And similarly, robots or machines have more than just acoustic sensors. They also have cameras that they can use when they're trying to learn the language that's used in their surroundings. So this work is all summarized in a paper that's on arXiv, so you can go and have a look there. I also have two repositories. The one is just for the DPDP AE-RNN on its own, and there I also do segmentation from phonemic sequences to just evaluate that in isolation. And the second repository is for basically all of the work that I described in the talk together, the VQ WordSeg repository. It's quite messy because there are so many moving parts, and I use a CPC model that's trained by Facebook, so it's a little bit messy, but it's all there and you can have a look. Thanks so much for listening.